So we're still working in 10.2. We're pretty much finished with 10.2 actually though. Are there any questions on homework 10.1 or 10.2? Okay, so the type of sequence or series rather that we were looking at last class, we were talking about these series that can be expressed or sequences that can be expressed recursively. And we said if they have a limit, we were just going to assume that the limit exists and then try to figure out algebraically what L was equal to. So this is directly related to that previous problem, although it's just a more generic thing. Because in our previous problem it was 1 plus 1 over, etc. This is just 1 plus b over. So our first term here, I don't think we'll work this fully out, but our first term is 1. And we see here, just like in that last problem though, the next term is defined as 1 plus b over the previous term. So if you're interested in working that out, you should come up with the limit as 1 plus the square root of 1 plus 4 times b all over 2. But the idea was that we assumed that the limit on the nth term existed and took the limit of the recursive relationship defined here. Did anyone have any questions on that type of approach? Yeah.
I actually did have a question on 10.2. If you
Okay, sure. Yeah, so that's pretty much the end of 10.2, so there. All right.
I think it was the last one, but I'll know when I see it. It was ridiculous, whatever it was. Yeah.
This one?
Yeah. I could do A, but not B.
Not B.
I couldn't find the exact equation.
Okay, so we'll check that out. 10.2, number 18. So it says use analytical methods to find the limit of the sequence. So we can, the first term is 0.15. The next term is the previous term times 1 minus the previous term. So let's just try to, starting here, we'll assume that we can find a limit as n approaches infinity. Call it whatever you want. And again, based on that assumption, if the limit of the nth, as n approaches infinity of the nth term is L, then also the limit on the n plus 1 term is L. Okay, so that means that if we take the limit of both sides of this recursive relationship, we'll have L equals to L times 1 minus L. This thing here. Let's start here, asterisk or whatever. Okay. So then we just try to see if we can make sense out of, does this limit actually make sense? So what are we're looking at L minus L squared. Yeah, so we have a quadratic in terms of L. Well, I guess, yeah, so when we subtract this over, we get 0, right? L squared equals 0. So that would suggest that the limit of this recursive relationship is 0. Is that where you were, or is that even the right question?
I haven't been able to find these puzzles.
Okay. So if this recursive relationship did have a limit, then it would be L. Okay. So I mean, I just glancing at this, it seems like it could make sense, right? Because if we start off with 0.15, and we say the next term is 0.15 times 1 minus 0.5, this quantity keeps getting smaller, and then the previous term is already small, and so the next term will be the small number times an even smaller number, right? So we would expect maybe that's intuitively, that's what would happen. Okay. Yeah, if you find it, just let me know. All right, and that's 10-2. In 10-3, we're going to look at a couple of different types of series. The first one we're going to look at is geometric. So your textbook really just starts out with the geometric series itself, but let's look at the geometric sequence, because we did say something specific about the geometric sequence. If the common ratio was, something in particular, then we had convergence. If it was anything but that, then the sequence, the list of numbers also would diverge. So the geometric sequences, I guess geometric sequences, these things are exponential-like, so you could view that like a continuous function, like 2 times e to the x or something like that. Remember this a here, since we start at 0, when 0 is in for n, that r to the n just becomes 1. Your first term is a. We'll go ahead and label these, because when we get to the geometric series, they don't change their interpretation. So a is the initial term; it's constant. R, as we've noticed before, is the ratio. That n could be viewed as the number of terms. And of course, that's for a finite geometric series, or sequence, rather. And the geometrics are monotonic. Whether they converge or diverge, they're converging monotonically or they're diverging monotonically. So I guess for number 1 through 4, let's identify the A, the R, and hopefully we remember whether or not that particular sequence would converge or diverge. So the example 1, what would our A be? A is your initial term, which is 1. The common ratio is what? 5. Each term multiplied by 5 gives us the next term. So we can see for sure that this thing would diverge, because everything just keeps getting multiplied by 5, right? I don't know. We'll just say for now that it diverges. Does anyone remember the geometric sequence? When a geometric sequence converged?
It's less, or the R's.
When r is less than 1, yeah, that's true. But it's not fully less than 1.
When it's greater than 0 and less than 1?
Not quite. It could be, we had those ones from, what was it, 10-1, where we had like a negative common ratio, but it still converged. So we can include positive and negative numbers as the common ratio to have convergence. So we'll just say that it diverges for now. Example 2, our first initial term is 10. The common ratio is what? 1/2. Everything is divided by 2. What do you think? Would this sequence converge or diverge? Converge. Everything is just getting smaller and smaller. We're dividing by 2. So converge. Okay. How about example 3? What's our common ratio there? Negative 1/3. So each subsequent term is obtained by multiplying by negative 1/3. Converge on a convergence or divergence there? Convergence.
Condition.
And example 4. What's the common ratio there? 1.2. Would that converge or diverge? Diverge? Maybe unsure about that. I'm trying to remember what it was. Maybe it's here. No. Be sure we talked about that though. So really, like to answer whether these things converge or diverge, we just kind of viewed it maybe intuitively, like, oh, this thing converges based on the number pattern. Really what we kind of focus on is the common ratio. The convergence or divergence of geometric sequences or series is dependent upon the common ratio. That was, I don't know, I forget exactly what it was. Yeah, here it is. So the geometric sequence in this theorem gives us for what values of the ratio the geometric sequence converges. So, you know, that's a fancy way to say what they're showing in this picture here, right? If the common ratio is less than or equal to 1, and remember this is for a sequence, common ratio is less than or equal to 1 but greater than negative 1. The geometric sequence will converge. So this is our geometric sequence. You know, it doesn't have the A attached to it, but if you remember from 10-1 or 10-2, where we said if you have a convergent sequence or a convergent series, and you multiply that by some constant number, like 10 or 100 or whatever, that constant multiplier does not change whether it converges or diverges. So, you know, just looking at this without the A, we have convergence in this interval and divergence otherwise. So if we go back to these for a moment, maybe, I don't remember if we talked about that or not, but if we go back to each one of these examples, then we can be totally sure, based on that theorem, our ratio here, larger than 1, converges. Ratio here, less than 1, diverges for 5. Converges for a half, converges for negative 1/3, and diverges for 1.2 because it's larger than 1. Okay, so really what we're going to end up doing is taking this theorem here and using that to determine whether or not we know a geometric series converges, and can we determine what a geometric series converges to. We've seen, I think, 2 examples where we looked at 1 over 2 to the k, and we looked at 1 over 3 to the k. And what we did there was we found the sequence of partial sums, and then we just took the limit on the sequence of partial sums. So do y'all remember those? Like, one of them had that diagram of the 1 by 1 square that was filled in with more smaller and smaller squares. Yeah. So that's kind of what we want to use the theorem here to kind of justify what we're going to do with geometric series. So geometric series is a times r to the n, and we're summing from 0 to infinity. Let's write out just the first few of these terms. When k is, sorry, this should be n, or the power on r should be k, whichever one you want to fix. So that's n equals 0. The first term then would be a. The second term is when n is 1, ar to the first plus ar squared, and so on and so forth. There's a times r to the n plus 1, etc. So just like we did with 1 over 2 to the k and 1 over 3 to the k, we came up with a specific formula for their partial sums. So just with those 2 examples, we might think, all right, well, if I'm given any geometric series, could I come up with a formula for the nth partial sum? And that's what we're going to do here, just as a very generic statement that we've written out up here. So the first partial sum for our geometric series is a. The second is a plus a times r. The third, a plus ar squared. And so we could keep writing those out, but in general, the nth partial sum, what would that look like for a geometric series as we're writing these out? So what would the fourth partial sum look like? A plus ar squared plus ar cubed, right? What would the fifth partial sum, what would the 10th partial sum, what would the nth partial sum look like?
It's just that, but you put dot 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 at the end, and then you put a r to the n.
Would it be the term before plus that one? So like AR to the n plus S minus R? Something like that?
I mean, we could express it that way, I believe, if I heard that correctly. But notice that the third partial sum, let's say, we have a plus ar squared. Notice the index here, our third partial sum, and we stop with summing at r squared. The second partial sum, we stop summing when r is to the first. The fourth partial sum, we stop the sum when it's r cubed. So this s sub n, when would we stop this sum? Yeah, the n minus 1 power, right? It's a times r to the n minus 1. Does everybody see that? So we stop there. Again, the 10th partial sum, we would sum all the way up to a r to the 9th. Right? Okay, so so that's the nth partial sum for our geometric series. And what we've looked at is for any particular infinite series, if you can come up with a expression for the nth partial sum and take the limit of that, you have the sum of that series. But looking at it this way, if n goes to infinity, it doesn't really tell us much, right? It would just say, well, that thing goes to infinity because it's just higher and higher powers of r. But then you've got to think about, well, what is r? Where is r, right? This r to the nth power doesn't always go to infinity, does it? It depends on where r is. So like if I said 2 to the n as n approaches infinity, then clearly that would go off to infinity, right? But there's my r. If my r was like 1/3, as n approaches infinity on 1/3 to the n, what does that go to? 0. So to answer this question, well, what's the limit on the nth partial sum? It really depends on where r is. But before we actually do that, the trick is, since we have all of these powers of r, is that we're also going to look at r times the nth partial sum. And then that way we can match up a lot of these terms. So r times our Sn is ar plus ar squared. Okay. So the reason we did that is now because we're going to subtract these two. We're going to subtract S of n minus r times S of n. And we see that most of the terms in those two expressions are identical. So when we subtract these two things from one another, most of these terms will disappear. So we're going to subtract the nth partial sum minus r times the nth partial sum. So on the right-hand side, what does that give us?
A plus AR to the n minus 1.
Okay, A. So is the A times r to the n minus 1 canceled when we subtract this from this?
Yes.
Yeah, so let's scoot this over. Right? It's kind of hiding there. This came from this term here that we didn't write out.
Yes.
So again, when we subtract those two on the right-hand side, what do we get?
A plus AR to the n.
Yeah, to the nth, not to the n minus 1.
See? Minus.
Oh yeah, minus. Yep, so we're subtracting those. All right, so most of those terms canceled, which was kind of the reason we did all of that. Okay, and then what we're able to do, since we have, over here on the left-hand side, we have an S sub n as in both of these terms. We'll just factor this S sub n out so we can solve for it, the nth partial sum. Okay. So then for a geometric series, the nth partial sum is a minus a r to the n all over 1 minus r. Remember, we haven't computed a limit as n goes to infinity, so what we should technically say here is that this is the explicit formula for the nth partial sum of a finite geometric series. And we'll look at like 2 examples of finding the sum of a finite, but we're going to continue with this because again we're dealing with an infinite geometric series. We want to know what is this? Is there a formula for the sum of an infinite geometric series? Well, we're off to a good start because we have a formula for the nth partial sum. So here's, if you remember from our previous section, the way we're going to view that is that the sum from k equals 0 to infinity of a times r to the n is equivalent to, the infinite sum is equivalent to the limit as n approaches infinity on the nth partial sum. And we actually know that because we just came up with the formula. Let's factor out the top, factor the a out of the top, rather. All right. So, does anyone have any questions at this point? Yeah, so just to kind of reinforce this nth partial sum formula, remember when we were dealing with this 1 over 3 to the k, and we said that the nth partial sum was, does anybody remember what the nth partial sum for 1 over 3 to the k was? Said it was 3 to the n minus 1 all over 2 times 3 to the n. Does that vaguely seem familiar? Yeah. So here, let's look at this. We've already dealt with this. Our a is 1. We have 1 times 1/3 to the k. So in this example that we've already looked at, a was 1 and r was 1/3. Now this doesn't quite look like this right here, but if we divide everything by 3 to the n, we get 1 minus 1 over 3 to the n all over 2, right? Or 1 minus 1/3 to the n all over 2. And that fits our formula here, the a times 1 minus r to the n. So we have 1, which is our a, times 1 minus r to the n all over 1 minus r.
Wait. Wait. Yeah, isn't r a third?
Was that our, guys think? Was that our nth partial sum?
Yeah, there's a just a little.
Or either that? Okay.
Very confusing. Oh, because it's 2 over 3.
Yeah, this is 1 though.
Yeah, but, oh yeah, never mind.
Should work here. Let's see.
Should be 2 parts and based on.
So that should be 2 over 3. 2 over 3? Yeah. I'll have to check that. I'll have to check into that. Yeah, I'm not quite sure. I can't see it immediately what's happening, why that wouldn't match up. Anyways, I'll come back to that. All right, so the limit on the nth partial sum is the sum of the series. And again, the geometric series is one of the few series that you can actually come up with an nth partial sum. There's another series that we look at in 10.3 where we can come up with the nth partial sum formula. But the rest of chapter 10 and 10.4 and 10.5, etc., are dealing with different types of tests depending on what kind of series you have. So it's not always that you can come up with an nth partial sum formula. But when you can, the limit is the sum of the series. And so we have to look at this limit here on the far right, kind of in light of this theorem here. So we've really got, I don't know, there's like 2 main cases that we want to look at. One of the cases is really 2 cases in itself, but I guess I started prematurely there. But we'll sort of break those down. I'll just take this and write it here, because this is sort of what we've already done. In order to find this limit, we need to view it in cases. So case number 1, let's look at when the absolute value of R is less than 1. So if we're, again, what this means is that R is less than 1 but greater than -1. So if this R here is in between -1 and 1, this R here, because all we're doing is computing the limit at infinity, that's the only thing that has the n on it. If that R is in between 1 and -1, what does R to the n approach or go to? Zero? Do y'all agree?
Yes.
If it's in between 1 and -1, or absolute value of it is less than 1, then it has to be some sort of fractional number, like a half or a third or 9 over 10, those kinds of things. So that R to the n, for our particular R we're looking at, would approach 0. And then that means that the limit just turns into a over 1 minus R. course, A is some number, R is some number. A over 1 minus R is just going to give us a number. Specifically, A over 1 minus R is what your geometric series converges to if the absolute value of that ratio is less than 1. So what we're looking at, A over 1 minus R, that is the sum of an infinite geometric series when the ratio is less than 1 in magnitude. The second case is when the absolute value of R is larger than 1. And really that kind of breaks down into two subcases, but I don't know that we need to look at both of them individually. This actually means that either R is greater than 1 or R is less than -1. So if the ratio is like 1.2, 2, 3, 5, 7, et cetera, or -1.2, -2, -3, -5. Okay. So in this particular instance, can we determine what this limit is? What would that limit be if R were where it's at? It would go off to infinity, right? Because this R to the nth power, you know, like, it's probably easier to think about them in a positive sense. If that were 2 or 3 or 5 or 10 to the infinite power, right? This thing is approaching infinity, so the whole thing diverges. So all of this, if absolute value of R is greater than 1, we have divergence. In other words, we don't have a finite sum. I think the other cases, if we want to look at them, they can be answered just by looking at the series itself. So I guess really case 3. Is when the absolute value of R equals 1, which again, that means either R is 1 or -1. So if R equals 1, then our series from 0 to infinity is just A times R to the K or A times 1 to the K. So what would that sum give us? What would that be? Would it converge or diverge? Remember, it's a series. Yeah, because the first term is A times K, 1 to the 0 plus A times 1 to the first plus A times 1 to the second. Right. So whatever A is, I don't know, it's just some constant. Maybe it's 2. Then this sum is just 2 plus 2 plus 2 plus 2, right? It diverges. If R is -1, our sum K equals 0 to infinity. A times -1 to the K. So what would the terms of that series look like?
A minus A plus A minus
Yes.
A.
Would that converge or diverge? If we add up an even number of terms, what is that series? 0. If you add an odd number of terms, what is the series?
Or A.
It's A, right? So this sum is either 0 or it's A. Does it converge or diverge? So the idea is like you can't really stop at adding an even number of terms or an odd number of terms, right? Because it goes on forever. So, but at the very basic idea of convergence is the same as a limit. In order to have a limit, you have to approach a single number. In order to converge to something, you have to approach a single number. So since this is 0 or a, depending on how far we are, it doesn't converge, it diverges. So I know that was sort of a lengthy process, but I'll summarize it with your the theorem 10.3. So that's our summary. Only one of those conditions converged. So we're dealing with an infinite geometric series whose ratio in magnitude is less than 1, then that series will converge, as we said, to a over 1 minus r. I think, so the examples I have typed out are for infinite geometric series. I do want to look at one or two examples of a finite geometric series. But I'll leave that up if you need to copy that for a minute. I'm going to add a new page. It's kind of a detour. So find the sum of the geometric series. So we'll go from k equals 1 to 5 on the series negative 2.5 to the k. So would that converge or diverge? It's a trick question.
It's finite.
It's finite, it's just going to converge, right? You're just adding up 5 things. The absolute value of the ratio applies to the infinite geometric series. Okay, so remember from the previous page, the sum of a finite geometric series was this formula we had before we took the limit as n approaches infinity. So that's the sum of any finite geometric series. Remember we said A was the first term, or the initial value, R is the common ratio, and we said N was what? The number of things or the number of terms that you add together. So you can write all of that out, but we really just need to identify our first term, A. Our first term would be what? Yeah, when k is 1, the first term is negative 2.5. Okay. The common ratio, R, is what? Negative 2.5 as well. And N is the number of terms or the number of things we're adding up. How many things do we add up if we go from 1 to 5? 5. if the sum, if it's small enough, like 1 to 5, you can just count on your finger. If it's 0 to 5, then you're actually adding up 6 things, but you can go 0, 1, 2, right? You can just literally count it out. The more, if they're really far apart, like if this was the sum from 3 to 145, the more generic way to find that is you take the upper minus the lower, and then you add 1 to that. Okay, so we have everything we need for our nth partial sum of this finite geometric series. So the nth partial sum, remember the nth partial sum, we should, I guess, because we know what n is now for this particular example. The fifth partial sum is the same thing as summing up the first 5 terms. So the fifth partial sum is a times 1 minus our ratio to the 5th power, because that's our n, all over 1 minus the ratio. Okay, so that's, I don't know, approximately negative 70.469. So that's the fifth partial sum, or the result of adding the first 5 terms of that series. All right, any questions on that? I wouldn't necessarily have a question like that on the exam, but I believe there are some homework questions. All right, let me just write this out. Let's look at maybe one more. Let's do the sum from k equals 4 to 12 of 2 to the k. So the first term, a, is what? Is what? Yeah, 2 to the 4th. Because we start with k equals 4. It's the first term. The common ratio r is equal to 2. And n, the number of things that we're summing up is how many? 9. From 4 to 12 is 9. Oops. So that's kind of how you, if like I said, if those numbers are further spaced out, you take the upper limit minus the lower, upper index minus the lower, and then you add 1. Okay. So we have n equals 9, r equals 2, and a equals 2 to the 4th. Which means we're summing up 9 of those things. We're looking at the 9th, the nth partial sum, the 9th partial sum here. I don't know if you want to leave it as this or this. But the 9th partial sum is a times 1 minus r to the n, and n is 9. So 1 minus 2 to the 9th, all over 1 minus r. Right. If one of these were on the test, I would probably just give you the formula for that. You really just need to know the formula for the infinite geometric series, that a over 1 minus r. Finite, not really that important. So that is 8,176. Now again, if this were an infinite geometric series, we know that it would diverge because our common ratio is larger than 1. Okay, so that's finite geometric series. Does anyone have any question on those? So a couple of these here, evaluate the geometric series or state that it diverges. So in example 6, we'll evaluate the series, but we can only evaluate it if it converges. Does example 6 converge or diverge?
Yes.
It converges, yeah, because R is equal to 1/2, and for convergence of an infinite geometric series, it has the absolute value of R has to be less than 1. So what is right here? And our series would converge to what?
6.
Yeah, A over 1 minus R. Remember, A is what?
1. 3.
The first term, yeah. So here it just happens to be 3 because we're starting at 0. But it's more, I think, a more general way to think about A is the first term of that series. A is equal to 3 and R is 1/2. So the sum of our series is A over 1 minus R, or 3 over 1/2, which is 6. Or if you want to write it up here, that's fine too. Okay, so it seems pretty straightforward, at least in that example. How about example 7? What's R in example 7? Negative 1/6. What do y'all think? Yeah, to the power of 5. So if you go back to how the geometric's presented,
So it's negative.
down here, where'd that go? Next page. So the geometric series, the sum from k equals 0 to infinity of a times r to the k. And notice it's just the common ratio r to the kth power, right? It's not r to the 5k or r to the 3k. It's just r to the k. So when we look at that, also worth pointing out, when k is 0, that causes our first term to be a, right? A times k to the 0. But in general, this a could be, like we said, it's just the initial value, or the initial term, rather. Here. So we don't want to look at this as negative 1/6 is our r because it's to the 5k. We want that 5 in there with the negative 1/6.
Yes.
So we're going to first rewrite this series. So it's 5 times negative 1/6 to the 5th, and then we can have all of that stuff to the k. That way we can see that's a times r to the k. So A is 5, or is A 5, I should ask. Is A 5? If this started at 0, it would be 5, right? Because all of that stuff to the k would be 1. But we're starting at 1, so the first term is when k equals 1, not k equals 0. So what is A? Yeah. Negative 5 over 6 to the 5th. Or, I don't know, however you want to write it. Same thing. So that's your first term, A. And then we've already addressed that R is not negative 1/6, but it's negative 1/6 to the 5th, or negative 1 over 6 to the 5th. Okay, so just be careful in how they're presented. If you start at 0 with a geometric, then A is always that number that's multiplying, but they don't always start at 0. Okay, so the sum, I'll just rewrite this. So that sum is A over 1 minus R. So we'll just write this here, A 1 minus R, we've got a 1 plus 1 over 6 to the 5th. And usually what's done here, you can just enter this in your calculator, but usually what's done is these complex fractions are changed by multiplying through top and bottom by 6 to the 5th. So if we multiply by 6 to the 5th over 6 to the 5th, equivalently we have that sum as negative 5 over 6 to the 5th plus 1. And let's see, it turns out to be negative 5 over 7,777.
I'm pretty sure we have something like that.
So that's the sum of the infinite geometric. Do you have any questions on that? Okay, so take a few minutes and do example 8. So what did you come up with for the first term? What is A?
Negative 3 over 8 to the 9.
Negative
That's it.
3 over 8 to the 9th. Do y'all agree with that? Negative 3 over 8 to the 9th is the first term. So the first term of here is when k equals to 3. Right, so it should be 3 times negative 1 over 8 to the 3 times 3. And remember, we're just looking at negative 1 over 8 as to the 9th, negative 1 to the 9th over 8 to the 9th. So, like, you know, there's multiple ways to look at this. I mean, maybe you didn't get that exact representation, but maybe you had one of those, right? Okay, so that's A, the first term of this series. Then what is the common ratio?
Negative 1 8 to the third.
To the third, right? Negative 1 over 8 cubed. Was everybody able to identify those? I mean, that's really what you need to identify. And here, again, we're saying that this particular geometric series converges since the absolute value of r is less than 1. The series converges. To that. So just make sure when you're doing these that you are validating that the ratio is in magnitude less than 1. Otherwise, this a over 1 minus r is not valid at all. Okay. So I'll just shorthand this. Our sum is that a to the 9th all over 1 minus r. So it's a really small number. You can get that from your calculator. I would multiply through, just to get a cleaner version of that, multiply top and bottom by 8 to the 9th. So negative 3 over 8 to the 9th plus, 8 to the 6th. So, I mean, it's a super small number. Whatever I think it's like, you should, I don't know how your calculator does this, but it's negative 2.308 times 10 to the negative 8. It's a super, super small number. But yeah, that's the idea. Any questions on the finite geometric series here that we've looked at? Okay, we will take a break and then talk about the repeating decimals sort of through the lens of a geometric series as opposed to kind of an algebraic standpoint. And then we'll talk about another type of series where we can find the nth partial sum of.
They were all. I cannot believe that. I absolutely cannot believe it. He lets you write your own stuff.
I think he said
You can charge for it, right?
three sheets that we three previous exams. He hasn't collected.
He even look at the last one that he said he would.
Now you just memorize.
So before we start this next example,
He doesn't even look at it.
there's another way to think about these geometric series. So we're just looking at it as a times r to the k. You could also factor this 3 out, right? Since that 3 is common to all of the terms. Okay, so we'll factor the 3 out, and then we could just work with this as our geometric series here, and figure out what it converges to, and then multiply it by 3. Right, so this is, oops, to the k. So that's A equals 1 and R equals to a half. So you could just deal with that as it is, and the sum of that thing is, well, is this. And then multiply it by 3. You get the same result. So if you want to deal with them that way, you can. Just be careful, where it starts and what your first term is. But if you can fit it as r to the k, then the same formula still applies. You can just multiply through by a at the very end. And again, that's seen here. If we just look at a 1 over 1 minus r and look at it that way, it's the same identical thing. So we said that earlier, right? Like if this particular series converges to a certain value, 1 over 1 minus r, then multiplying something that converges by a constant doesn't change the fact that it converges, but it does change what it converges to, right? It doesn't change convergence, however. So, anyhow, the repeated decimals as a geometric series, and then as a fraction. Like we saw with the previous examples from 10.1, I believe, you just want to look at the repeating part. So our geometric series is going to represent the part of that fraction that repeats. So maybe we can look at that one second. So like example 10, similar situation. You have the 0.456 that's repeating. So I don't know, if we said that the first term is 0.456, or as we're calling it A, then the next term that we have to add to that would be, we would have to take this here. Let me just write it out. We have to take this plus 0.000456, right, plus, put all this in here. So that, if we expand it out and look at it as a sum, that way we can look at it as a geometric series. So we still see the first term is 0.456, but to get to the next term and the next term, etc., what does r have to be in this here, in this thing?
A over 1,000.
1 over 1,000, right. So just look at it as we're from 0.456 to 0.000456. We just had to put another 3 zeros behind the decimal. That's 1,000th, right? Same thing here. To get to the next term, we had to put these 3 zeros behind the decimal. So that's another 1,000th. Okay. So we can express that as a geometric series. Is that all right, what we've done, or are there any questions? So then we want to express 0.456 repeating as a decimal. And so what we'll do is we'll just say, well, here's a geometric series where the absolute value of the ratio is less than 1, so we know it's a convergent geometric series. In particular, we know it converges to A over 1 minus R. So all of this stuff, this sum is equal to our A. And let's write it as 456 over 1,000. So that's our A over our 1 minus R. and then multiply top and bottom by 1,000. So we end up with 456 over 1,000 times 1 minus 1/1000th times 1,000. So we have 456 over 999. So that's how we would represent 0.456 repeating as a fraction. Any questions on that example? So just right here, this is A over 1. All right. So then going back to example 9. Again, the geometric series is the part of that fraction that repeats. So we have to take this 5.12 and sort of separate it out and then work with it later. So we're going to say that this is equal to 5.12 plus 0.0083 plus, what else? Just write a couple of these terms out. Yeah. 0.000083 for that. Let me just color this a little bit differently. So we're so on and so forth. And that's the geometric part that we have in blue. This is our geometric. So the first term of that geometric is 0.0083. Or we could write that as as 83 over 10,000. And then the common ratio here in the geometric is what? One over 100, do y'all agree? 1 over 100 from next term in the geometric to the next. We're just putting 2 zeros in front of the 83 or 2 zeros behind the decimal place. So 1 over 100. So you're just make a note or something, mental note. Since the absolute value of r is less than 1, the geometric, there'll be an infinite geometric in blue. The infinite geometric converges again to a over 1 minus r. So what we have is our 5.12 plus the sum of that geometric series that converges, which is A over 1 minus R. So we want to express the whole thing as a fraction. So we want to deal with the 5.12 separately than our sum here in blue. But the sum here in blue, again, what we'll do is multiply top and bottom by 10,000. I'll just write it here. So we get 83 over 10,000 minus 100. And then that's still plus our 5.12. And I guess you can deal with that whenever you want. Is everybody all right with what we're doing? Any questions? So we'll keep our 5.12 plus our 83 over 9,900. We want to express the whole thing as a fraction. So then we've got to express the 5.12 as a fraction and add it together with this fraction. So 5.12 as a fraction is what? $512 over 1,000 plus 100.
100.
Yeah, exactly.
Did you say 100?
No, it says 1,000, but I know.
Okay. All right. So over 100, two places. We've got that plus our 83 over 9,900. Yeah. So common denominator, I'm going to multiply all that out. 50,771 all over our common denominator. So that 50,771 over 9,900 is 5.12. 83, 83, 83, 83. I think that was it. Let's check. Yeah, that's what I guess. I guess that's as far as it'll go, but you get the idea. How far Google will go. On the same level of accuracy there. But anyhow, that's how we can write those as fractions. A kind of geometric series in disguise. So just a different way to think about those repeated fractions. I don't know if that's pertinent to real life stuff, but cool nonetheless. Okay, so that's those two kinds of things. Did anyone have any questions on the geometric stuff? Because we're going to shift gears a little bit.
Why do they call it geometric?
Huh?
Why do they call it geometric?
Just because it's the ratio, have you heard of the geometric mean? I'm not quite sure why they call those things geometric, but it's based on if you take a square and then expand it, by a constant factor, you can kind of get a visual. Like if you remember that picture of the 1x1 square where we had all those little squares in there, if you keep incrementing by a half the other way, you can turn those tiny squares by multiples into a full square. So it kind of, it's the expansion, the multiplier expansion kind of thing.
Does that have to do with geometry?
I think in a visual sense, yeah. I'm not sure if it has ties to like, you know, geometric postulates, side angle side, any of that kind of stuff. But I think it's more of a visual expansion or contraction, which really could just be considered multiplication or division. But yeah, I don't know why they call it that. So the other kind of series that we can find a nth partial sum for are these telescoping series. And when you think of a telescope, think of a really old school like pirate telescope, ones that like fold out and fold in, you know, like not modern telescopes. So the idea of a telescoping series is that, you know, you start off with this thing that looks infinite, this giant thing, but it actually ends up contracting into a couple of things. That's kind of the idea. And really there's no explicit formula to say, all right, well, if you have this telescoping series, the formula is going to be X, Y, Z. It's really just a matter of writing out the terms, seeing which ones cancel, and then what you have left over is your nth partial sum. So you just want to write out a few terms at the beginning of the series and a few terms at the end of the series. And keeping in mind that we're after the nth partial sum, so we want to go out to the nth term, right? If we go out to the nth plus 1 term, we're getting the n plus 1 partial sum. If we stop at the n minus 1 term, we would get the n minus 1th partial sum. So we want to definitely go out to the nth term, but how many in the beginning and how many at the end is really up to you. You really just want to see what the pattern is for this particular series. That way you know what cancels and what stays. So we're just going to write out the terms of this series in these pairs as they are explicitly given to us here. So when k equals 1, our series is 1 over 1 plus 1 minus 1 over 1 plus 2. So that would be the first term of the series. And then just let's look at a couple more. Plus, and I'll write here, this is when k equals 1. When k equals 2. So the next pair, I guess, or next term of the series, when k is 2, 1 over 3 minus 1 over 4. So far nothing is, so far one thing is canceled, right? You've got a negative third plus a third. So I don't know, maybe we want to look at just one more of these. When k is 3. We have 1 over 4 minus 1 over 5. I'll have to write it down here, run out of room. But I think that's the first few terms is sufficient. We'll write out the last few terms. Remember, again, we're stopping when k is equal to n. We're after the nth partial sum. You know, after you see a few of these, you might not have to write out as many terms. So if we're stopping at the nth term, then the previous term is when k equals to n minus 1, and the previous to that when k equals to n minus 2. Is everybody all right with that? I know it's weird to have k equals n kind of thing, but we're just stopping at n. All right, when k is n minus 2, what is our term when k is n minus 2? 1 over n minus 2 plus 1, which is 1 over n minus 1, yep. 1 over n minus 1 over n. When k is n minus 1, we have 1 over n minus 1 plus 1 minus 1 over n minus 1 plus 2. Is everybody all right with what we're doing? We're just plugging this n minus 1 in for this k. This is n minus 1. This is n minus 1. Okay, and then when k is equal to n, we've got 1 over n plus 1 minus 1 over n plus 2. So the only reason we're able to write out the nth partial sum for these types of things is we can see a lot of these things will end up canceling with one another. I would recommend, I mean, maybe it's obvious to some, maybe not, but I would recommend writing out the assignment on how things cancel in some way, shape, or form. That way we can just keep track of what we're getting rid of. So the cancellation, I mean, you don't have to write all of this out or anything, but just something to keep track of what's canceling. And I would just start here. I would say that this clearly is going to cancel with this when we add them together. So I would keep them in pairs for sure, and I would say, all right, well, within each pair I'm just going to call the 1/2 the first and the negative 1/3 the second, but corresponding to each pair of things. So however you want to describe that, I would just say that this second cancels with the first, and it's the pair to the right. So however you want to like keep track of that. So I'm just going to write the second cancels with the first one to the right. And that way when I get further on in my tail, I know which thing cancels exactly with which thing. And I don't have to guess, well, is this thing really left over or did it actually cancel with something? But also that cancellation gives me the reverse, right? I could also say that the first in this pair cancels with the second in the pair that's to the left. So you get kind of a twofer. So the first cancels with the second on the pair. First term cancels with the second term, one to the left. So however you want to look at that, those things are canceling. So just going through the terms, the negative 1/4 will cancel with the positive 1/4. Does the negative 1/5 cancel? Yeah, the negative 1/5. Here we would say, well, that's the second in the pair. The second in the pair would cancel with the first. That's one to the right. We just didn't write out the next term that's to the right. So this thing is canceling with the very next thing over here. And so on, we would continue on in that direction until we got to our, n minus 2, n minus 1 in our nth term. So the 1 over n minus 1, does that cancel with anything? Yeah. So again, just you've got to think about these terms that we didn't write here. ... That's the first canceling with the second. That's one to the left. This will cancel with this term over here that we didn't write down. So that's gone. The 1 over n cancels there. The 1 over n plus 1s cancel here. And does the minus 1 over n plus 2 cancel? No, because those things canceled with 1 to the right. There's nothing to the right because we stopped at the nth term. So actually, if we were going to write out that entire sum, what would it be? Yeah, that's it. It's just 1/2 minus 1 over n plus 2. Since we added up n things, the 1/2 minus the 1 over n plus 2 is our nth partial sum. So let's just, I ran out of room here, we'll write it here. Thus, the nth partial sum is 1/2 minus 1 over n plus 2. So what's the sum of that series? Somebody say, what? Yeah. Remember, if you have the nth partial sum, the sum of the series, the sum of the infinite series rather, is just the limit on that nth partial sum. To 1 over n plus 2, of course, goes to 0. So that entire infinite sum is just 1/2. All right, do y'all have any questions on this? So then, an example like in example 12 and example 13, initially they don't look like telescoping series, but I don't know, if you remember this 1 over, we've got a simple linear times a simple linear, right? So we could do a partial fraction decomposition to see if that were telescoping. The thing with telescoping series is it has to be, it kind of has to be the form this something minus something else, right? Because that minus is what's giving us the cancellation in a lot of those terms. So if, like on example 13, if you were to do partial fraction decomposition and you got like A was 5 and B was 2, then there's no way those terms are going to cancel. But if you got like A to be 5 and B to be -5 or something like that, right, then you would expect some cancellation. So since we've just talked about this, it doesn't look telescoping as it's presented. But if we can try partial fraction decomposition here. All right, we'll do that in a moment. We did already mention that, so we'll write that down and come back to it. So example 13, we'll do partial fractions to see what it gives us. Hopefully it gives us something that's telescoping. How about example 12? Rewrite it as, right, yeah, so this is just a simple property of logarithms to rewrite that sum as k equals 1 to infinity, the natural log of the numerator minus the natural log of the denominator. So there's a chance that things will cancel because one's positive, the other is negative. And then again, unfortunately, if you think it's telescoping, you just got to write out a bunch of terms, see if things cancel, because you got to know what cancels in particular. Okay, we're starting with k equals 1. So the first pair, ln of 3 minus ln 2. The next k equals 2, ln 4 minus ln 3. Do we want to write out another term, or is it okay like that? Okay. Plus. I'll write it down here. Remember, there's stuff over here too. So how many terms do y'all want to go out? We've got to stop when k equals n. Do we want to go back 2 or 1? 1. Okay, so we'll stop at when k is equal to n, and then we'll go back 1 to the n minus 1. Maybe need some more space back here. So when k is n minus 1, we have the natural log of n minus 1 plus 2. Can I write it like this? Natural log of n plus 1 minus the natural log of n minus 1 plus 1. And then when k equals n, natural log of n plus 2 minus natural log of n plus 1. So our cancellation here, we have, we can look at it in 2 ways, but these 2 terms are canceling. So if we say the first pair here, that first term cancels with the second term in the pair that's 1 to the left, to the right rather. And then we can flip it around. The second in each pair, second term in each pair cancels with the first of each pair if we look at it 1 to the left. Okay. So then is the negative ln2 going to cancel with anything? No, the negative ln2 will say, and this time I'll just underline what cancels, that way we don't have like, it's not too messy. So the ln of n plus 1, does that cancel with anything? So the ln of n plus 1, that's the first in each pair, cancels with the second, that's to the right. The second term to the right here, second. Minus ln of n, does that cancel with something? Which one does it cancel with? To the left. So this will cancel with this one over here. The ln of n plus 2, does that cancel? So what we have left over in our sum is just the negative ln2 and the ln of n plus 2. So I'll just rewrite that here. K plus 1. Yeah, k plus 1. All right, so that's the only 2 terms we're left over with. It really just depends on how far your terms apart and how many cancel. Sometimes you could end up with a telescoping series that actually had 4 or 5 terms that didn't cancel, but the idea still remains the same. We have the nth partial sum. Sorry, let me scoot this over. Fail. I could probably fit that in there. Nope. Sorry. We have to compute the limit at infinity on that. So we forgot that. Okay. So what is that limit? Infinite limit right? The natural log of infinity is infinity. And all that means is what? That the series diverges, right? What was the other one? The other one that we looked at here, it converges to 1/2. So not only do we know if it converges, when we can find the nth partial sum, we can explicitly state what it converges to. As we'll see with most of these series in chapter 10, the best we could say is this thing converges or it diverges. In most instances, we wouldn't know what it converged to. There's only two particular series that we know what it converges to if it does converge. That's the telescoping series and the infinite geometric series. So those are the only two we can say with certainty it converges to this value. The other ones we just say it converges or diverges. Okay. Any questions on that example? All right. So like we said, this one initially as it looks isn't a telescoping series, but maybe it is after we do the partial fractions. So we'll look at the 1 over the k times k plus 2. And what's the setup for that, for partial fractions?
A over k plus b over k plus 2.
Right. A over k plus b over k plus 2. So we have 1 equals to a k plus 2 plus bk. So if k is 0, then we have 2a equals 1. So let's just say this, if k is 0, 2a equals 1, or a equals 2.5. And if k is negative 2, then we have negative 2b equals to 1, or b is negative 1/2. Which means 1 over k times k plus 2 is 1/2 over k minus 1/2 over k plus 2. So then after we rewrite that in terms of partial fractions, you see that it is a telescoping series, just like the last two have been. So this thing here, we start at 1, yeah, it starts at 1, k plus 2. All right, so now we have it in the form, a telescoping form. So I think there's two ways to look at this here. One is just leaving the 1/2s in there, but the other way is that we can look at it as just this 1/2 times the series. Then we can just look at the series that we have in brackets, find the nth partial sum, take the limit, then multiply everything by the half, or you can just keep the half in the entire process. It's really up to you. I don't know. I'm just gonna look at this right here, and then multiply it by half. Okay, so we're right at the terms of that series, and see if it, see what we end up with after we cancel things. So first term is 1 minus a third. Second term is a half minus a fourth. So no cancellation, we want to keep going. Third term, 1 over 3 minus 1 over 5. So we do have a cancellation there with our negative 1/3 and our positive 1/3. So that's probably as far as you need to go out. Once you've noticed a cancellation, that's all you're after, is the assignment of what cancels with what. So we have this. So how many terms at the tail do we want to use? We want to use when k equals n, and what else? N minus 1 and n minus 2, because we see that the cancellation happens, 2 pairs away. So if we're stopping with k equals to n, we want to go 2 pairs in the other direction. Does that make sense? If you're unsure, then just write out a bunch of terms. It's not very efficient, but get you there. So this is when k equals n minus 2. We'll look at when k is n minus 1. Okay, n minus 2, we have 1 over n minus 2 minus 1 over n. When k is n minus 1, we have 1 over n minus 1 minus 1 over n plus 1. And when k is n, 1 over n minus 1 over n plus 2. Okay, so then cancellation happens here and here. So I guess what we're saying is the second term will cancel with the first, but that's now the pair that's 2 to the right. And the first cancels with the second. That's 2 to the left. So then we can determine, does the 1 cancel or does the 1 stay? Does the 1/2 cancel? Stays. Does the negative 1/4 cancel?
Yes.
Yeah, it cancels. It's the second in the pair. The second in each pair cancels with the first. That's 2 to the right. So this thing will cancel with this one here. So that one's gone. The negative 1/5, also gone. How about the 1 over n minus 2?
Yes.
Yeah, it cancels with the second that's to the left here. So that's gone. 1 minus n, 1 over n, negative 1 over n are gone. 1 over n minus 1. Yeah, this one again is the first. It's canceling with the 2 to the left, so it's not canceling with that one, but it's canceling with, oops, 1 too many. This one over here. This one right there. Yes, right there. All right, so that one's gone. Negative 1 over n plus 1 stays, and negative 1 over n plus 2 stays. Okay. So what we have left, we have a 1, a positive half, negative 1 over n plus 1, and negative 1 over n plus 2. Again, that's the nth partial sum. Sorry, I might have written that down incorrectly for the last one too. But we're just going from 1 to n on that. And then we take the limit to make that an infinite series. So this infinite sum corresponds to the limit at infinity. Okay, so the limit on that thing, whatever we call it, is 3. So we got 3 halves for the telescoping part, but remember we took out the 1/2. So that's not our ultimate final sum. Our ultimate final sum is the 1/2 times that, because we took the 1/2 out. Okay, questions on what we've done there with that telescoping? Okay, so then we just need to put that back here. For this one here, let's see. There. So then the sum of that series is 3/4. This is kind of like our side work here. Does that make sense? Any questions on what we're doing? Why we're doing what we're doing? So there's a lot of this development that, granted in later chapter 11 rather, we don't actually use all of it, but I do just want to show you like what all of this is building up to. So you might have remembered from Calc 1, if we look at a linear approximation of the sine function near 0, that it's pretty much the line y equals x. So like a lot of times in optics or physics or whatever, when you've got a really small angle measure, instead of using the function sine, you would use the function x, right? So that's our linear approximation. What series allows us to do is eventually we're going to say, hey, this infinite series is converging to this function of x. So we will see an infinite series that converges to the sine function. But that's why we've got to build up all of this, all of these tools to determine when something converges, how do we know it converges, how do we know it converges to a particular function. All of that kind of stuff is, we're in the slow development of that right now. So anyways, here's our first degree polynomial approximation of sine at the point 0, 0. But if we increase that to the second degree polynomial, the sine is an odd function, so it wouldn't be approximated by an even polynomial. It's only when we get to the third degree. Now we see sine is a little bit better approximated by this cubic polynomial, and even better approximated by this fifth degree polynomial. So just look at the region around the origin and how much of that particular function covers up the sine function. Here at 1, it did an okay job, right? You see the difference though pretty soon out. But when we look at this fifth degree, now we're even further out. Now we're out here at -2, +2 before we start to see a difference. I might be able to find a better one, but if we go out to 15, maybe it'll do that. Maybe it won't. This one might be better. Okay, so here's the third degree polynomial that's approximating sine at 0. Yeah, this one does better. So you see, as we keep getting more and more degrees in there, how the sine function is more and more overlapped by that polynomial. I mean, I don't know, that's pretty cool. But that's why we're going through all of this. We're going through the trenches with sequences and series, so we can develop the language to say, how do you approximate a function with a polynomial? That's the bigger picture of what we're doing. And then also, when we can approximate a function with a polynomial, then you can actually start looking at, like definite integrals from 1 to 1.5 of functions that don't even have antiderivatives, like e to the x squared. If I can represent e to the x squared, for instance, as a polynomial, I have 1 plus x squared plus x to the 4th over 3 factorial, something like that, right? Then I can just integrate this polynomial, because I don't know what the integral or the antiderivative of e to the x squared is. I know it's this polynomial, and I know how to find the antiderivative of each term of this polynomial, right? Same thing with limits. Like limits are it's less useful for limits, but the whole point is I can take a complicated function and rewrite it as a simpler function, which is a polynomial. It's an infinite polynomial, but nonetheless it's a polynomial. All right, that's the bigger picture. I'll see y'all Thursday.